bit of background about uniform circular motion. So when we're talking about uniform circular motion, we can think of it here on Earth as being the same as horizontal circular motion. So our object is not having to deal with going downwards with gravity and then battling up against gravity. So obviously it would be, if it was vertical circular motion, the object would speed up when it's moving with gravity and slow down when it's fighting against gravity. But we're not talking about that, we're talking about uniform or horizontal circular motion. With an object, if we look at it from above, and I've been using in class my examples of my school key, if it's travelling around in a circular motion, even if I'm spinning it at a constant rate, we know that the speed will be constant. However, its velocity will be constantly changing because we know velocity is a vector quantity, so therefore its magnitude as well as direction. So whilst the magnitude, the number of its speed, so it might be 1 meter per second or 3 meters per second, whilst that stays the same, the direction is constantly changing, therefore the velocity of my key is constantly changing. So at this point here, we could call this time equals 0. If it's travelling clockwise around my circle, that at this moment here, the velocity of my object, draw a tangent to the circle, will be whatever magnitude it is in that direction. As my keys spin and come over to this position, just to choose a position at random, as it travels around and it's travelling at this point, at that very moment, if we draw a tangent to the circle, it's going to be straight up. Its velocity is going to be whatever magnitude it is, straight up, using this diagram here. So, if the velocity is always changing, we know, therefore, there must be acceleration. A changing velocity means acceleration is occurring. So, how can we work out the direction of this acceleration? Well, what we can do is use vector addition. So we know that change in anything is final minus initial. That's what mathematically what this delta sign means. So if we're wanting to find our change in velocity, it's going to be our final velocity minus our initial velocity. And so if we're working with these two positions that we have here, we'll call this our initial and this our final over here. So let's use our two vectors and find the change in. In fact, what we'll do is we'll choose the position here, so we've gone through less of a turn. This will just make our lives a little bit easier and make the description clearer. So at this point in time here, the velocity of the object is whatever magnitude it's going to be, depending on how long it takes to go around the circle, but it's going to be straight down. So this is our initial. Let's call this one our final. So let's take these vectors down to here and deal with them. So our initial is like this, and our final is straight down. That's supposed to be straight down. This is, and this is. Okay, so let's find out what our delta V is. So we can use vector addition. We get our final vector and we add a negative of the initial vector. So what we're going to have to do is to make a negative of the initial is to reverse the direction of this one. So we keep our final as being the same, and we have negative initial is this. So we're adding these two vectors together. So let me rearrange them. I'll drag my final over here, and my initial so that they are head to tail. They're the same in magnitude, so I should be making them exactly the same length. Okay, to find the change in, adding these vectors, and I complete my triangle from the base of the first to the head of the second, and so this is my delta V. If I take this vector back to my diagram, put it like this, and we show that it points for the period from here to here, the average acceleration is inwards towards the center of the circle. And this is in fact what always happens, is that as an object travels around in a circle, the change in velocity, or the acceleration, is always inwards towards the center of the circle. Let's go one step further then. If we have an acceleration that is greater than 0, and we do, we've found that we do have an acceleration, this means that our net force also must be greater than 0 newtons, because according to Newton's second law, so our object clearly has a mass, it has an acceleration that isn't 0, so therefore it must be experiencing a net force. And the direction of the net force is the same as the direction of the acceleration. These are vector quantities. So therefore what that tells us, that if I redraw my circle here, and I had my initial and my final, this was my change in velocity, which is therefore the same as saying my acceleration. This also gives me the direction of the net force. So what this means, in summary, and this is the one very important point to remember with uniform circular motion, is that the direction of acceleration is always inwards towards the center of the circle. And the same can be said for the net force. The direction of the net force is always inwards towards the center of the circle.